Now let's understand what is the normal modes of vibration. Okay, so we know that the standing wave on the string, and I am assuming that you understand the basics of standing waves on the string. Okay, so that's why I am not going to talk about the standing wave on the string. Okay, so we know that the standing wave on a string can vibrate with different frequency, right? Yes. So for each frequency, the string wave vibrates with different mode. Okay. Yeah. For each frequency, the string wave can vibrate with different modes, and we name these modes like the fundamental modes, like the first harmonic, second harmonic, first overtones, second harmonic, second overtone, third harmonic, second overtone, all these things we will be discussing. So don't worry, don't panic. I am here. You will understand each and everything. What is the harmonic? What is the overtone? What is the fundamental frequency? What is the fundamental? Okay. So don't worry. Okay. So let's start with the very basics. That is the fundamental mode. So fundamental mode means the minimum frequency, the minimum possible frequency with with this frequency, the string wave can vibrate, or string wave can be formed on the string. This is that frequency that we call, and if the string wave is vibrating with this frequency, we call this mode as the fundamental mode. Okay, fundamental mode. I think you should be clear. Okay, so I told you that I am going to discuss about the string that is fixed at both ends. If let's say this is a string, you can see the diagram. Okay, let me make this string and here. So see, this is a string. Sorry. This is a string. It is fixed at both ends because I am going to discuss only about the string that is fixed at both ends. So this is fixed here at this end, and this is also fixed here at this end. Okay. Now if it is fixed here, it is fixed here. That means here nodes should be formed. Here nodes should be. Again, I am assuming that you understand the basics of standing waves because all these things, nodes and antinodes, has been covered in the standing wave video. If you haven't understood the standing wave, then you can watch my video on the standing wave also. Okay. Now, so if we have to, if this is a node, this is a node, and we have to make a standing wave that is vibrating with the minimum possible frequency, then the wave will be formed like this. Okay, like this. Okay, and we understand that the distance between node and node means the distance between two consecutive nodes is lambda by. Okay, fine, we understand this, sir. Now I am saying that the length of this string on which the string wave is formed is capital L. So we can clearly write L is equal to lambda by 2, right? Yes, right. So from this we can also write lambda is equal to 2L, right? Right. Great. Now we know V is equal to F into lambda, where V is the velocity of the wave, F is the frequency of the wave, and lambda is the wavelength. So from this we can write F is equal to V upon lambda, right? So F is equal to 1 upon lambda, and V can be written as C upon mu. We again know the formula of wave on the string, that is V is equal to root T upon mu, where T is the tension, mu is the linear mass density. Great. So now I am calling this equation 1, means lambda is equal to 2L. So from equation 1, I can put the value of lambda here from equation 1, that is 1 upon 2L root T upon mu. Okay. Now let's move to the original slide. And this is the original slide. So we got this formula, right? We got this formula that we just tried. Okay. So if the standing wave or the string is vibrating with this frequency, with this frequency, this F equal to 1 upon 2L root T upon mu. If the string wave is vibrating with this frequency, we call this frequency as the fundamental frequency. Okay. Or we also call this the first harmonic. This is a terminology. So you have to remember this terminology. Okay. And there is a logic behind this terminology. Why I am calling this first? Because here you will understand a little later why I am calling this a first harmonic. First, for now, the string is vibrating, or the standing wave is vibrating with this frequency 1 upon 2L root T upon mu. And this is the minimum possible frequency by which a string wave can be formed on a string. Fine. Now let's move to the another, and that is the second harmonic or first. Don't worry about the terminology. I will make everything clear. For now, focus what I have to deliver. Okay. So now I don't want the minimum possible frequency. I am saying I have increased the frequency a little bit. Okay. And again, I have increased the frequency, but I again want the standing wave to be formed on the string. Okay. I again want the standing wave to be formed on the string. So again, but the string is fixed at both ends. So if the string is fixed at both ends, that means at the end point, again the nodes will be formed because it is fixed at both ends now. So if I have increased the frequency a little later and we want the standing wave to be formed on the string, then it will make two loops. Okay. Okay, great. If it will move two loops, then let's analysis this. Okay, let's say this is a string, this is a node, and two loops has been formed. So again, this will one another node, this will be node, this will be node, and again the length of the string is same because we are taking the same string. We are not changing the string. If we are not changing the string, then two things will not be changed. Length will not be changed, and the linear mass density, this mu will not be changed. Great. So L can be written as lambda by 2 plus lambda by 2 because we know the distance between two consecutive nodes is lambda by 2 and lambda by 2. So lambda by 2 will make 2 lambda. So lambda is equal to L. Again, I am following this equation. Again, we know V is equal to F lambda. So from this, we know that F is equal to V upon lambda. So lambda, we can put L in place of lambda, so 1 upon L, and we know V is equal to T upon mu. Okay, but can I write it as I have multiplied 2 here and 2 here, so I can write it 2 by 2L root T upon mu. Is it okay? Right? I have just multiplied in the denominator and numerator by 2. Okay. Okay, now let's get back to the original slide. So right now we have got this equation, right? Right. So I am calling now. See, observe the pattern. In the fundamental mode, we observe that here it is 1. Okay. Now in the next mode, we observed here it is 2. Okay, now let's do the analysis of one more mode. Then the picture will be clear. Okay. Now I again want the standing wave to be formed, but I have further increased the frequency of the source. So now again the string is fixed at both ends. String is fixed at both ends, and at the end point node should be formed. Okay. So now what shape the string wave will take now? So this is the shape the string wave will take now. Node endpoint at endpoint node will be formed, and two more node will be formed also. Great. Again the string is same, so length and linear mass density mu will be same. Great. So if this is the case, then it is clear that L will be equal to, again we know the distance between two node points, it is lambda by 2, and lambda by 2. No problem in this. So lambda by 2 plus lambda by 2 plus lambda by 2. So we will get 3 lambda by 2. Or we can write lambda is equal to 2L by 3. Again we know that V is equal to F into lambda. So we can write F is equal to 1 upon lambda. F is equal to V upon lambda. So F is equal to 1 upon lambda under root T upon mu. So if I will put the value of lambda from this equation, then we will get C upon 2L T upon mu. You can calculate. This is an easy calculation. So again, we have achieved this equation. You can see that is written in blue color. So we have achieved this equation. Okay. Now again observe the pattern. In the fundamental mode, we were getting 1. Here see, we were getting 1. In the first harmonic, in the second harmonic, we were getting 2. In the third harmonic, we are getting 3. Okay. So now you can observe the all other terms are same. 12 in the denominator is present in every mode. Root t upon mu is also present in every mode. But what is changing? The number that is present in the numerator. So now if I have to write, so that's why I am calling this the third harmonic. Because why? Because here third is present, because number 3 is present in the numerator. That's why I am calling this the third harmonic. And I am calling this second harmonic because here number 2 is present. And I am calling this first harmonic because number 1 is present. Okay. Now we also call these first harmonic, second harmonic, and third harmonic. Like the first harmonic, we call this fundamental frequency. Why? Because this is the minimum possible frequency by which the standing wave is getting formed. That's why we call it the fundamental frequency. And we call the second harmonic the first overtone. Okay, this is just a terminology you have to remember. And again, I will tell you the logic. So for the second harmonic we call the first overtone, and the third harmonic we call the second overtone. So if you understand which harmonic is this, you automatically understand which overtone is this. Just subtract 1 from the number of harmonics. If it is third harmonic, subtract by 1, then you will get the answer 2. That will be the second overtone. If you are getting fourth harmonic, then it will be third overtone. If you are getting fifth harmonic, it will be fourth overtone. Fifth harmonic, it will be fifth overtone. Okay. So now if I have to write the journal formula, means for the nth harmonic, so for the third harmonic, I am getting 3. For the second harmonic, I was getting 2. For the first harmonic, I was getting 1. So for the nth harmonic, I have to put here n. All the other terms in the formula will be same. Means in the new denominator 12 will be there, and root t upon mu will also be present. Okay. And this formula is very, very important. I am star marking this formula. Just remember this formula. If you remember this formula, you can easily calculate which harmonic or which overtone is this. And this formula is valid when the string is fixed at the both ends. Okay. So just keep this in mind because it may create confusion. So just keep this in mind that this formula is valid for the string that is fixed at both ends. Now, this n is representing the harmonic. So this will be nth harmonic. And if I have to calculate the overtone, then what I have to do? I have to just subtract 1 from this n, then I will get n minus 1 over 2. Okay, n minus 1 over 2. I hope you have understood this